Today, we're going to talk about enterprise MLOps. I think a lot of people have a lot of interest in ML now. Companies are building machine learning models. You have a lot of job opportunities in this space where companies are hiring ML engineers and data scientists and things like that. But one big challenge out there is like, how do you get like all your experiments, all your Jupyter notebooks, models and things like that to production? That's still a big pain point in the enterprise. So we're going to talk about this. We'll walk through a scenario. We'll discuss all the possible stumbling blocks along the way that you could encounter if you're trying to build a model and things like that. So to get started, a little bit about the company I work for. I work for MavenCode. We're like an artificial intelligence solutions company out here in Southlake, close to Sabre. We do a lot of things around ML, basically helping companies get their models into production. We do stuff on-prem and in the cloud. We're Google Cloud partners as well, so we do stuff with Google, basically helping a lot of our customers on the Google Cloud landscape build their models, deploy things on the Google Cloud, on Google Cloud. We do a lot of things around document processing and understanding using AI to extract content out of documents and things like that. And some of the stuff we've done is across different industry verticals. So to get started, I just want to level set while people are joining us, just play a quick video so that we can just know the impact of AI around us. AI touches every part of our life from the time you wake up, believe it or not, that you're interacting with an AI device. It could be your Fitbit, Apple Watch, and things like that. So I'm just going to tee up this video while people are getting in. Then on the other side, we'll talk about the agenda and we can get going. Can everyone see my screen? Good to go? Okay, I think so.
I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies. And studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs. Identifying diseases like leukemia from a simple drop of blood, even in our own homes, and finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses. And a learner, discovering new strategies from complex games. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Yeah. Thank you. Um, so I'm gonna show this one real quick. It's quite over. So believe it or not, AI is around us. AI is basically going to affect everything we do in our day-to-day lives. We do AI, and there's a need to do it responsibly. There's something called responsible AI, which is around making sure whatever you do it well because it touches people's life. Things like self-driving car. You have low margin of error. So if you're doing things, you want to make sure that your models are accurate, that your processes are well defined, and things like that. So today we're going to go over machine learning ops. So this is the agenda, overview of what you do as a machine learning ops engineer, the roles and responsibilities, because there's a myth out there that people think they can just hire data scientists or just convert some software engineers to like data scientists and you can get your models out. Um, we've seen that in some organizations and things like that. And we'll go through the entire landscape, all the process you go through to develop a model and get things out. And we'll discuss a use case. So we grab a data set from Kaggle. One of the interns working with us, they basically put this together. So a big shout out to them. So we'll walk through the use case. We can discuss things. We'll go through all the steps and processes you go through to create a model, and now you get things from like your notebook to production and stuff like that. So it's a deep topic. We'll try to like go as deep as possible. I imagine we're not going to cover a lot. So one of the things I told Jim earlier was that we might just come up with a sequel where we just go in and go into more details on some of the other aspects that might interest people. So there's a Slack channel out there. Even after this presentation, if we didn't cover what you think you're really interested in, you can go on the Slack channel, chime in, and I'll be there to like answer some of your questions as well. So overview of MLOps. Um, a little while ago, as far back as 2014, Google researchers published a paper around ML. Because I believe it's like around this time in 2014, people started appreciating the need for like building models and stuff like that. And people build algorithms or trying to get it into production. But Google, they've been there forever. Google is like an AI company. So they really pointed this thing out. And I'm going to highlight the part that really caught my attention there. Most of the technical depth around building ML is not just about building the algorithm. That's probably the easiest part, believe it or not. The most difficult part when you're trying to get your model into production and it's going to affect or impact people's life is the whole process around it, which is the MLOps process. How do you like make sure that the data you're feeding to your model is the right data, is not obsolete, so that you don't create things like data drift or implicit bias. How do you retrain your model? Because over time, if you don't retrain your model and you're training on stale data, the model may not be performing well in production. How do you monitor all these things to make sure like you're getting a constant feedback and things like that? So a lot of all those things are technical depth that goes around the process of creating a model and getting it from just what you have on your notebook into production. So it's a very essential, a very important topic. So if you look at the graph, in the last few years, the interest in MLOps has grown a lot. Especially in the last 2 years, it's a big deal. A lot of companies now realize the advantages of having ML as part of their all organizational initiatives and plans, but how do you get these models into production? That's the challenge. They hire data scientists, they hire smart guys out of college, they build all these interesting algorithms, but getting it into production on time and efficiently is really a big deal. And the reason for that is like MLOps is not easy. Just like you can call it a rocket science, just like launching a rocket is not easy. You go through different stages, especially now that everybody's trying to go into space. You're building all these fancy rockets and you want to make it reusable. But You can launch a rocket, but you need to make sure that your rocket gets into orbit, gets into space. You have all these stages that you need to make sure things go through, and you want to be able to repeat that process over and over. And that's where the challenge comes in. You don't want to just build something and you can't reuse it, because the whole idea of software engineering is for you to build something. You have the initial sunk cost, and over time, the cost goes down to zero. But it's not really that easy in ML, and that's why people are trying to look at ways of doing things a lot more better with MLOps. So we go around, we consult in this space, and we see a lot of companies like they have things. They say things like this. I think this is a very popular tweet from Jim Barber from I think IBM. It's like a lot of companies. I mean, you go to companies like, oh, it took me 3 weeks to develop my model. It's been 11 months. We still can't get it into production. And on the average, 40% of the companies says that right now they say it takes more than a month to deploy their ML models. And believe it or not, most ML projects fail, not just because the algorithms are not good or the guys out there don't know what they're doing. It's just because there's not a well-defined ML process out there. So what is machine learning operations, or what we call MLOps? It's basically a process to simplify the process involved in deployment of machine learning models between the operations team and the machine learning researchers. So your machine learning researchers are data scientists, they're not DevOps guys. So you can, I mean, someone who's a statistician, or you can imagine them trying to get a model to production, which is what happens in a lot of all these organizations where they hire data scientists, they think they can solve all this problem, but in reality, that's not the case. So it takes more than a data scientist to get a model into production. So we can say with MLOps, the goal, especially in the enterprise, is to standardize and streamline the machine learning lifecycle management. So there's a lifecycle to like ML process. You gather your data, you make sure the data is right, you transform the data into features that you want to fit into the model. You train and develop the model. It's not necessarily like your first model that will be right. You still need to like create a lot more models, and you select the best model. Then you get a model into production, and you inference against the model. You do A/B testing, validation, and things like that. You make sure the results are good enough. Over time, you need to redo this over and over again, because your data is changing, and you need to constantly retrain your model because your data is changing and things like that. So all those things are what we call the model management lifecycle. So if you're like in an enterprise where you don't have a process for this, it becomes, it's going to become very difficult to manage. So the goal is to standardize and streamline the process. So in essence, you can say like ML ops is going to be a critical component of any enterprise trying to do successful ML projects. And the reason for this is like ML projects, like I said earlier, most ML projects fail not because the algorithms are not good or the models are not right, but because people don't have the process are not in place yet in most organizations. So in order to mitigate and avoid this risk, it's better to have a good ML process in place where you can always identify all these possible risks, and now you can work against them, and you have a process kind of like in software engineering where we now have a DevOps process, and you can easily build your application, create your software, do unit tests, you run it through your CI/CD process. The only difference, like with ML ops, it's not just your code that is changing, your data is changing, you're creating model output artifacts, you're changing your algorithm as well, which is your code. You have all these variables coming together, and you need to monitor things and make sure you're doing it right. So in the enterprise, the major challenges can be summarized under these four categories. Number one is reproducibility, which is like it's not easy to reproduce an ML model. So think about it this way: you're working on a notebook, and you write your algorithm, everything works for you. You need to have a pipeline that can basically it can run over and over, because every time you run your model, your pipeline, after going through multiple iterations, your results are always going to be different. So how can you create a reproducible pipeline that you can run over and over? So those are part of the challenges. And it's easy if you think about this just in terms of just one model, but in a big enterprise where you have probably hundreds of thousands of models that you need to get into production, how can you efficiently reproduce your process? The other part of it that we see a lot is the reusability of your components, your pipeline components. You're building all these models, you're creating all this cool stuff, but can you make it into a reusable component? We're not there yet, and that's part of the things that you try to standardize with MLOps, kind of like the way software engineering around object-oriented programming helped us create things like APIs. Can I have that kind of API thinking around my model components where if I have a component to train a model, a component to pull in the data, I can glue it all together and create a pipeline? Can I share this with my teammates so that if my teammate is working on a component, if I've worked on a component, I can share with my teammates and they can grab it and use it rather than trying to go through the same thing over and over again. Um, so those are the challenges you see working or consulting in this space, especially in the enterprise. The other thing is the manageability of your output artifacts. So you're training models, you're creating, every time you create a model, you want to version it. You want to version your pipeline so that you can track things and see what you did. Like, okay, I ran like 5 experiments. This is a pipeline. This is a model output artifacts. This is how everything looks right now. Can I basically have this version so that I can go back and after doing like 10 runs, this is the right pipeline that I need to use, or this is the right model output that I need to use. A lot of all those things are not there yet, and that's one of the things that MLOps tries. I mean, MLOps, a good MLOps practice, will try to solve in an enterprise. And finally, once you have all these things in place, you want to automate your process because right now if you're building the models, you have it running on a GPU instance or CPU instance. And sometimes you keep it overnight, you run it, you come back, you're burning some GPU or CPU cycles because the model ran to completion a lot more faster than you thought and things like that. So how can I automate my process so that kind of like we have in CI/CD, I'll keep referencing the traditional software practice where you have a CI/CD process that runs end to end. You can trigger a build every time you commit to source code. How can we have that in a model development lifecycle so that whenever you're checking your code, you can trigger a build, or whenever you have a fresh data source, a fresh data set coming into your feature store, you can trigger a build and the system runs and it creates a new version of the model. And once you have the model, you can do things like model scoring so that the best performing model gets selected and deployed into production or QA. And you can have your model auditors or risk managers assess the model behavior and performance and make sure everything is working appropriately. So those are the challenges for big enterprise, especially if you're in a big industry where you need to be responsible with the output of your model. You can have your model just provide a lot of false positives because the models, like we saw in the video earlier, can impact people's lives. So you need to like make sure whatever the model is saying is right and good enough. So so let's go to the second stage where we'll talk about the roles. So the general belief is like models. I mean, in an enterprise, you just need to like just whip up a code, bring up your Jupyter notebook, especially if you're new to this field out of college. It's like, oh, I can just write it up in Jupyter notebook and do image segmentation or classification and stuff like that. But it's a lot more than that if you're like a Tesla or a big company doing things around image detection and stuff like that. So that's the general perception for people that are new to this space. But in essence, like I said earlier, there's a lot of technical depth around ML, which is like you have things like data verification, making sure you have the right data sets. You do a lot of configuration, data validation. You do a lot of feature extraction because let's face it, when your data comes in, it comes in different forms and varieties. You need to make sure that you extract what you need, and that's what you fit into the model. So a lot of all those redundant data sets, you need to like do away with it and get whatever the model needs and feed it to the model training algorithm. So, and On top of that, when you're trying to get into production or QA or dev, you need to do like check to make sure you're not like spinning off GPUs or servers and you're not using the right resource management. And serving infrastructure, once you're done, you have your model, you want to do model serving and stuff like that. And you want to monitor, understand what's going on. At the end of the day, you want to be able to like analyze all these things and see, is the model producing the right results? Is the results coming out from the model good enough to where you're certain that if you put it out in production, it's not going to create any damage or any harm. So a typical MLOps team now is evolving to look like this, where you have not just the data scientists like people think. I can just gather my data sets and dump it on the data scientists and they're going to do magic with it. You still need the subject matter experts, people that have been in the business for a long time. They understand what's going on. They understand what you're trying to do based on experience, so that if something goes wrong, they can call you out and say like, okay, your model output is crappy. You got to fix it. Then you have the data scientist, of course, which is it's like a premium job right now. Everybody wants to become a data scientist. And you have data engineers that work hand in hand with like data scientists to basically provide the data sets, operationalize the process, making sure you're getting the right data and stuff like that. Then the ML engineers, which they work basically on the integration aspect of the models, making sure you can do things like model serving. You have your model deployed correctly. And you still have your traditional DevOps guys that basically work and conduct things around your CI/CD integration, making sure the infrastructure in place, and a position that basically is very relevant that but people don't talk about it a lot the let me get my pen. The model risk auditors, especially in companies like in the finance space, insurance, where you have people actually going through the models. You don't want to create a lot of false positives, especially in healthcare. You don't want to predict someone has a cancer if they don't, and all those things. So you have model risk managers and auditors going through the models, analyzing the output. They do a lot of back testing to make sure things coming out of the model is actually right before you put it out on the field. And a very important aspect of this as well is the ML architects responsible for the whole infrastructure, how things talk to each other, and stuff like that. So to paint a better picture of this, this is a typical workflow in any ML project, and we're going to go into more details when we go into the landscape as well, where you have a subject matter expert that come in with like all the business questions, like, okay, how can we increase our revenue based on X, Y, Z, or what can we do to increase the conversion rate of people coming to our website to do Y, Z. They basically create a problem you want to solve, or they discuss the business need. Then you go through you develop models, and to do that, it's not just a data scientist. You have data engineers working with the data scientists. Data engineers basically trying to see how they can gather all the data sets from all your data sources and things like that. Because let's face it, in most organizations, the data is siloed away in different places. You have some data sitting in message queue, databases, file systems, and things like that. And you need to like prepare this data in the right format for your data scientists to use it. So you have the data engineers trying to acquire the data. They do the data prep, a lot of ETLs and transformation. You do feature engineering so that you have just the components you need for your model training. You have all those feature vectors in place. And the data scientists can now take this and create a lot of experiments. You run the experiments, you do model evaluation and compare the results. The subject matter expert comes in at that point in time and check what you're doing. Okay, does it make sense? Is it adding up to what we expect, or is it just a waste of time and effort? So they come in and they do a lot of kind of like a feedback, self-correcting mechanism in that place. And once you think everything is okay, then you now want to prepare for production. So you basically have a QA environment where you can stage things out. So at that point in time, you involve your ML architects, where you now need to start thinking about how things are going to look in production. If you have this as front facing where customers are interacting with it, So you have your data engineers involved, ML architects, your software engineers on the team, thinking about how you deploy these in the environment and things like that. And you think about things around scalability of the application. How do you scale it? It's one thing for you to just write your algorithm in a Jupyter notebook, and it's just you running it against a few sets of curated data. But once your model gets into production and you have 10,000 people trying to access it every second, how do you scale? How do you handle things like that at scale, which is some of the problems that people at Google have solved and things like that. How do you basically continuously roll out new versions of your model and things like that? So those are the things you think about, and at that point, you have your ML architects, data engineers, software engineers working with you to like solve that kind of problem. And once you've deployed your model into production, you it's not the end of the whole show. You still need to monitor the model and see that the model is providing the right results. There's no false positives, things like model drifting because your data is still, or you're not fitting the model with new data and things like that. So you have your model risk managers still keeping an eye on your model and your pipeline to make sure things are going okay and nothing is failing. So those are the kind of things that you want to put in place whenever you're trying to build an ML team in an enterprise. It's not just the ML and data scientists or data engineers alone. There are a lot of people that contribute to the success of your MLOps pipeline or MLOps project. And those are the benefits you get working with companies like Google. They've done this a lot of times, and they have a lot of engineers in this space that can probably explain this based on what they do day to day. So we'll go through the MLOps landscape right now. So a typical MLOps project or pipeline, ML project looks like this. You have a bunch of data source. Your data source could be coming from a streaming source, it could be a message queue, it could be any streaming source or Kafka pops up or things like that, or if it's an IoT application, it could be coming from RabbitMQ. And you have your batch data source, which is like you just get a dump of data coming in, maybe from your data lake or your warehouse. All this data comes in. So the number one thing you want to do whenever you're training a model is to make sure you have the right data source. So once you have your data, the next thing we do, and it's universal across any ML projects, you get this data, but they're not in the right form that you need for your model based on what your data scientist says he or she needs for the model. So you do a lot of feature engineering, which is like you bring in the data, you transform it, things like encoding the data sets, and all those things fall under transformation. So you look through the data, you see what you need, what's not relevant, and if there's any outlier that you need to drop, or if there's any field or columns or attributes that you don't need. But you go through all this feature engineering step, and we're going to go into details maybe in some other talk down the road. But feature engineering is a very important topic around ML ops and ML in general, because if you get your data, the features that go into your model wrong, it's just garbage in and garbage out. So the model is never going to be accurate, and you don't want to create a model like that and put it out there. So the goal of building a successful ML pipeline starts around this place, which is like sourcing the right data sets and extracting the right features that you need, which is a feature engineering step. And once you've done that, you can now start thinking about your model training. So you take all these features, the input vectors to your model, and you do a lot of trainings. So your first model will necessarily not be the most accurate model. You go through several iteration. You do something called hyperparameter tuning, which you try to tune the model and make sure that you're getting the right accuracy depending on your objective function. You might want to have your model be be very accurate. So in that case, your end goal is like I want the most accurate model, and you can have different objective functions that you're optimizing to get. So you have all these features that come in, and you train your model. And you run multiple iterations sometimes, and once you think you have the best model, you have different versions of the model as a result of this process. So you should have something around model versioning. So that means the model comes in every time I train a model. I want to track the version, I have the metrics around the model performance. If my objective is to have a very accurate model, I have that version of the model. I will record the metrics, which is the accuracy. And you can go through that process and produce maybe up to 10 models and stuff like that. And all these things change every time your data sets changes. So every time you have a new data set, you run the process, you create a new model, you tag it, you version it, and stuff like that. So once you have that in place, the next thing is now deploying the model. So that's where you consume the model as an end user. So we want to do things like model serving, which is you build your model, you put it out there. You can do things like A/B testing just to make sure the model is performing the right way. And you can, once you have it out there, you can now have your software engineers integrate with it through like maybe a web service endpoint, or it could be a batch process where you run this bunch of data against your model and you try to get a result. And while you're doing this, you want to keep logging all the things you're doing, like how many requests are coming into the model, what's the throughput, how can you, I mean, at what point do you need to scale the model and things like that. So you monitor all these attributes, and that way you can know when to like go and trigger a process that will run the pipeline again, because you're testing your model to make sure it's still relevant. You're not getting a lot of false positives. So while you're getting that, you basically want to trigger the process if you think something is wrong. So part of the automation stage of this pipeline process is to know when you need to trigger a new pipeline to run and generate all these new model artifacts, promote the model to production and stuff like that. So in any ML project, you're gonna get a pipeline similar to this, if not exactly this, and this is the kind of process you go through. And the goal is to standardize this process so that it's always you can always repeat it. So it's not like something you're running from your Jupyter notebook and you can't scale it out. Or if you're on vacation, your colleagues should be able to just click and run your pipeline and everything just run off the bat. So those are the challenges of ML, and that's what we're trying to solve with MLOps. So I'll go to the next slide, which basically shows you a typical workflow for an ML engineer, data scientist in any enterprise as it is right now without all this process in place. So if you're like a data scientist or ML engineer and your organization is not fully embracing MLOps, this is what you see. You wake up in the morning and you get to work, and it's like, oh, I need data. I need to like build a model, and your task will like sourcing from the data, and the data can be anywhere. So the first job you're trying to do is like, okay, what do I need to do? Do I need to get the data? You're doing the feature engineering, and to complicate the problem in most organizations, they try to do like they have a multi-cloud strategy. So they're not just running on Google Cloud; they're running on Amazon, they're running on Azure, and sometimes on-prem with things like Qflow. So it becomes very complex as an ML engineer or data scientist to deal with this. So, but these are the kind of problems that MLOps try to solve. And Google has a product called Vertex AI. I'm going to talk about it briefly. They just released it like a month ago that tries to simplify all these things as well. So your typical workflow looks like this. You're interacting with the storage. You're trying to pull all this data, normalize it, create it into a form that your model needs, and you basically run it in your computer environment, which is either a GCP, a GPU, or CPU. And you're managing a lot of all these things yourself. This is a lot of cognitive load and just a resource, a few resources, because the spectrum of knowledge around these things is a lot. So it's better a data scientist does what they know how to do best, which is like building the algorithms around the model and not worry about this. So to complicate it, if you have a big team in an enterprise, things get a little bit more complex. You have different teams doing things in different ways. Most organizations they're like in a silo. They're pulling the same data sets. They're not sharing data, and it gets a lot more complex. You have different clouds, and things just get chaotic and stuff like that. So, what if we think about this? If you're trying to build an MLOps process for your organization, you can now start thinking about how you can abstract this. So there are two things basically you're doing whenever you're doing ML. You're pulling data from a data store, and you have a GPU or CPU that you're using for your compute. That's the bottom line of what you're doing. So there are two buzzwords out there right now. If you're in the ML space, there's something called the feature store, which from feature engineering, you can deduce that. So the whole idea of a feature store is for you to like compute all the stuff that a data scientist needs so that they're not the one doing all the ETL. So across the organization, you have different data sources and everything. What if you have a pipeline that basically pre-computes all the data sets I need to train my model? So a lot of all these companies right now, that's what they're doing, especially companies trying to do things around MLOps. You basically compute all the data sets you need. The data could be in BigQuery, it could be in S3 bucket, it could be in a database or a data warehouse or stuff like that. You pre-compute all those things and you put it in a feature store. Feature store is part of the Vertex AI that Google just released. It's a very important component of it as well. So you can pre-compute all your attributes, all your feature vectors, and put it in this feature store. The other thing is like Kubernetes is pretty big out there right now. So for things that are running on the cloud, you can containerize your ML workload and just run it on Kubernetes. And there's a project out there that Google primarily spearheaded called Qflow. It's a very important ML tool out there, and we use it a lot. So with Qflow, you can basically containerize your training algorithm and put it on Kubernetes, and you can basically deploy it and run it. You can run multiple instances, you can run multiple experiments and things like that. You can create a pipeline that you deploy and runs on Kubernetes. So there are a lot of feature stores out there, but one important one that Google just rolled out is the Vertex AI feature store. It's a managed service, so that means you don't have to worry about the underlying infrastructure. You can leave that to Google; they'll take care of it. So you basically create your feature store table or entity where you want to store stuff, and you can start ingesting data and dropping it in your feature store. And there are other ones out there. There's one called Feast, which is open source. It runs on GCP as well. And there's a Databricks feature store, which I've used before. Databricks just rolled it out. You can basically compute your features and put it on the Databricks feature store and have all your attributes ready for your model and things like that. So Vertex AI, I think it's kind of like a spin-off of Qflow because a lot of the guys at Google working on Qflow basically shifted to Vertex AI, I think. So, but you can see a lot of similarities between what you have in Vertex AI with what you have in Qflow. Things like pipelines, the endpoints, which is like serving and stuff like that. So you can think about it as a managed service as well for your Qflow. So in Qflow, you have to worry about Kubernetes, bringing up the infrastructure, containerizing your workload, and all those internal metrics of Kubernetes and all this YAML. But with Vertex AI, Google has created a lot of abstractions around this. So you don't have to worry about the underlying internal mechanics of how things work and how things integrate. All those things are handled for you by Google, and you can just focus on what you want to do. So you can ingest your data to the feature store, run your training model in the notebook, and once your training model is done, you can create your pipeline in JSON format, upload it, run your pipeline. You can trigger and schedule a pipeline run with cloud functions and things like that. So it's a very interesting idea. I think Google learned a lot from Qflow, and a lot of all those things are implemented in Vertex AI. So I think everyone should check it out. We're exploring this as well as a team out here. So I'll dive into feature store right now. But Jim, do you have? Are we good on time? Do we want to take a break? But if not, I can keep going.
Yeah. Do you know how long this next section takes?
It's not long, probably like 10 minutes.
Okay. Yeah. If you'd like a break, we could take a quick break. Otherwise, yeah, we're good and we can keep
If we're
rolling.
good, we can keep running it. Yeah, I'm
Yep.
good. Yeah. Okay. There's some questions out there as well. We can take it during the break. Okay, so I'll just dive a little bit into feature store from a high level perspective, and we're gonna go into this some other time. I think Jim can get me back. We can talk about feature engineering and how you prepare your data for feature store, and we'll talk about the way it works in Vertex and the other open source alternatives. But the whole idea of feature store is like if you're training a model, you need a set of input. So a feature is a measurable, observable attribute that is part of your input to a machine learning model. So the way a model works is like you show it a bunch of stuff, and over time it understands those stuff and it can predict based on what it has seen before. So one of the challenges in ML is like learning is an ongoing process. Every time you see something, you learn something. That's what's called experience. So in ML, a lot of organizations they have all this data siloed in different locations, and you can't just go in and pull all this data all the time for every data scientist and run the process over and over. Number one, you have the cost associated with that, and number two, it's just going to be a lot of stress on the system. So the whole idea of feature store is to create a store where you can just have all these feature vectors that you need, which are all the sets of inputs that you think you need for your model training. So what you do is like you prepare these features, you put it in a table in the feature store, and you can connect to it, and you run your model training. So if tomorrow, we have a new set of data sets, I'm not going to go in and run all the ETL process again. All those things will be computed and scheduled to be in my feature store, depending on how I'm acquiring my data. So you're not doing a lot of SQL join. Um, Aggregation and everything all the time. You need to pull all this data. Everything is already prepared for you and it's ready for your model to go. So all those attributes and feature, which is called feature vector in this case, they're already available to you in the feature store. And your model, your algorithm can just feed on it. You train your model, you get a result out. So that simplifies a lot of problems for you in your MLOps process or MLOps pipeline. So the features can come from different sources. Like I said, it could be from your raw data store, um, databases, data lake, and things like that. Like that, it could be from a streaming data source. If you have an IoT application, or if you work for Uber, where you have a lot of data coming in from your customers every time they try to hail Uber traffic and your drivers on the road. And you can have a spike or a surge period where you have a lot of data flowing in and you have a few data coming in and things like that. And it could be like an aggregate of various raw inputs, and you try to derive a feature vector that is relevant to your model. So instead of, let's say, passing in a username, first name and last name, maybe you do a lookup with an email and you get a user ID and you send it in and stuff like that. If you're dealing with sensitive data around your customer that you don't want to expose during your training process. And the other thing is like you can window in your data. So it could be like, okay, I'm having a lot of data flowing in. Can I just create a window where I can just do a roll up, compute what I need, feed it to the feature store, and I can use it for my training. So features change over time, and that's the whole idea. So it's like a time series. So you can think about it as an ongoing event that keeps going forever. So every time you have a new set of data sets, you compute it, you put it inside your feature store. And so there's a time component to it that always matters where in cases where you need to go back and train. So let's say if you're working for a company like Sabre, you're trying to build a time series data and you're trying to build a model with the data sets from the beginning of the year to now. You can build a model with that. But if you want to train a model on data sets for 2020, you can always do a time travel and just train on the range of data within that period. So you have all these things organized for you. You're not just trying to go do a pull, aggregate, join, and all those crazy SQL all the time. Whenever you need to train a model, you have a time series component that represents all the snapshots of data that you've ingested in your feature store. You can time travel and slice and dice through all these data sets. So it makes it a lot more easier for data scientists, especially if you're trying to compare things over an historical period of time. You can easily slice and dice through this data and do whatever you want to do, compare things within those windows. So feature store in MLOps, goes without saying, makes it easy to operationalize your ML workload. You basically don't have to do a lot of all those joins and aggregations and everything all the time. Your data management becomes a lot more easier. You can just run a section of your pipeline. Your data scientists have constant access to pools of data that they don't have to like go over and call you every time they want to do an ETL. And you can share your feature store between different model training pipeline for your team. So instead of having team A, team B, and team C pulling the same data over and over again and creating a lot of stress on your system, you have everything aggregated in the feature store. And the team can just go in and pick whatever they want, and they can run on that. And team B can go in and do whatever they want as well. So it creates a lot more sanity to the, if you want to say that, in a big organization. Then, like I said earlier, you can version and track changes easily. So if I'm training a model and I notice like, okay, in the last few months, the models we're training right now, their accuracy is not as good as the model we trained last year. What happened? I can easily like time travel through my data settings. So like, okay, the last 4 models were trained based on data we got in the last 4 months, and this is the accuracy we're getting. But before then, we got a lot more accurate model, and so we can now easily triage and see what's going on, what changed, what attributes is contributing to all these things and making things a little bit more difficult. So the fact that we can easily track the data set that we're using for training with the algorithm, with the pipeline, and the model output makes life a lot more easier and things like that. And it creates a lot of consistency between your training model and serving and the model you serve. So, um, uh, so the way I can explain that is like sometimes whenever you're training a model, you create all these features and you have the model. By the time when you're trying to inference against a model, you don't have the feature vector that you use to train the model, and that's what the model is expecting for inferencing. So they call it online. So just before you send in your data to the model, you're going to transform it to a feature vector. And if you have a feature store, you can basically just send your raw inference data to the feature store. It does a lot. It does a transformation on it, gets the output transformation, sends it to the model, and you have your inference result out. So they call that online feature store. So if you have basically, it's kind of like you have, let's say you have an email and you have a recommendation model, and the recommendation model is expecting a user ID. So if you've created a feature store, you can just send the email and do a lookup on your feature store, get the ID, and send the ID to your model for inferencing. So it basically simplifies that. So that's one of the advantages of feature store. So this is a typical way of getting data into feature store. One of the ways we've done it is to have a Qflow pipeline. It's part of the Vertex AI stack as well. They use it to like create the pipelines. So the pipeline basically creates an abstraction, and from that abstraction, you can have components on each stage, and each stage of this component. Let me get my mouse. Each stage of these components are basically they're Docker containers, for those of us familiar with Docker. And that's how you create a pipeline. So this pipeline is like a container. We're connecting to a Kafka data stream. And once we get the data in, we want to validate. So we have a schema validating the data just to make sure we have the right columns, we have the right attributes. If the role is for us to drop roles where the data are not like accurate, we can easily drop a role if we think we're missing stuff. Depending on the role, you can validate on schema. And depending on your process, we pre-process the data and make sure the data is okay. Then we just write it to our feature store and stuff like that. So that's what this process represents. So you have a feature store writer and then writes it to your feature store. So with Vertex AI, you can do something similar to this as well. This was done on Qflow. So you can ingest your data, you transform the data, you make sure you have the data in the right format, and you push it into your feature store. And that process can now be scheduled. So if you're on Google Cloud, you can use something like Cloud Scheduler to like trigger a process, like every like hour, compute my data, get it out there. Or you can have if your data is like file is on something like Google Storage. You can say every time a file lands and it's been up to 5 minutes, you generate an event, you trigger a Cloud Function event, and you basically trigger your pipeline to run on the feature store. So I'm going to talk about Qflow because that's what we've been using for a while. And I'm going to just talk about Vertex, which is very interesting. I will encourage everyone to check it. And if we give us, if the next time we talk about this, we're probably going to focus heavily on Vertex, which it's a new product from Google, came out like 2 months ago. And it basically does a lot of things that Qflow does. And it's all managed. So it's one less thing for you to worry about because everything that has to do with the underlying mechanics and plumbing, it's already handled by Google. You just bring your data and you focus on what you know how to do best. So it's a big problem solver for MLOps practitioners. So, I think I showed this slide earlier, but what I'm trying to get to here is to solve the challenges of MLOps, Google came with a project Qflow that allows you to run containers on Kubernetes, and now they have Vertex AI. So, but I'm going to touch a lot on Qflow, which is what we've used a lot. So, the whole idea of Qflow is for you to like containerize your application right out of the box. So you gain things like composability, where you can treat each component as a Lego block. You saw it earlier in the feature store. You can use those Lego blocks to create a pipeline. You can connect it together the way you want, and it's portable. So even though you're building all these components either on-prem or just build your local, you can easily shift and lift it across all the major cloud providers and things like that. And you can scale it because it's all containers. You can auto scale it. You can scale out your underlying node pool and scale out these containers as a result. So Qflow is a very interesting project, and a lot of the knowledge from that is what Google is using to like build up on Vertex. So Qflow is kind of like a machine learning toolkit. It's a toolbox that allows you to like build your ML components and get it into production a lot more faster. And you can basically integrate things and create a pipeline that runs your model end to end. So to keep it simple, it helps you simplify your model development lifecycle. So this is like the toolbox in it. If you're building things on Qflow, you have different parts of the components that you want to use for your model training. You have a Jupyter notebook, your hyperparameter tuning with Katib, the chainer, different components, and it's an open source thing, so it becomes a little bit uncontrollable sometimes because people are just adding things. So that's why something like Vertex is really helpful, where you can control things, even though it's a little bit opinionated, but it's a little bit more controlled. So Qflow has a lot of components for you to do things, and they call it operators, and you can have these operators running on Kubernetes. So once you've installed Qflow, you have a UI that looks like this, where you have your notebook, your TensorBoard, your experiments, your pipelines, your runs, and stuff like that. So I think I have a dashboard for running a cat job and stuff like that. So you have a dashboard and everything around that. So in an enterprise, if you're running your workload on Qflow, you probably have something like this, where you have your data scientists and your team. You can collaboratively share notebooks. If you're running a TensorFlow job or R or Python, PyTorch, you just run everything in a notebook. You can share with your colleagues. You can have a team namespace. They have a concept of namespace, and you can just run your workload in your namespace and get your results and see if it's good enough. You can share it. If not, you can go through multiple iterations and stuff like that. And you can run all these things on any infrastructure running on the Google Cloud or any of the major cloud providers. But just to touch a little bit more on Vertex, it's the new kid on the block, and it does a lot more of what Qflow does in a very fine way. That means you don't have to worry about the underlying infrastructure. It basically leverages on Google ecosystem of machine learning toolkits. So you have things like vision, audio, language translation, and things like that that Google has done, and they did it well. So that's part of the AutoML toolbox. You have it with Vertex, and you can integrate with it through your API call. They have a feature store built in there, so that's a lifesaver. So instead of you worrying about like your feature store, in a database or using something open source, Google has created a feature store where you can just create all these attributes and feature vectors and drop it in there and stuff like that. For if you're curating your data, they have the data labeling and you have the training and you have an endpoint for prediction. And one thing that's really important right now, especially for model risk auditors and managers, is responsible and explainable AI. But if an AI model is, you want to make sure you can understand what it's predicting and explain it in terms of why is the result this way and things like that. So they have toolkits as part of Vertex that allows you to do a lot of all those things and stuff like that. So if you want to look into that, I think there's a code lab. I'm going to try to open it out there around Vertex. HTTPS. That just is out there. So you can check this out. It's kind of like an overview to Vertex released by Google as part of the code lab. So basically, introduction to Vertex allows you to like do things around kind of like what you're doing with Qflow, but in a lot more elegant way because it's all managed and orchestrated by Google. And you basically use your Qcloud commands, log in, authorize, and you can start creating your pipeline. Once you log into your Qcloud console, you have access to Notebook. And once you have access to Notebook, you can install all the libraries you need and start building up your pipeline. The cool thing about this is like it's based off of the Qflow SDK. So if you're familiar with Qflow pipelines, the same SDK is used in Vertex to like generate the pipeline artifacts. So there's a lot of like parallels between the two. So you can create your pipelines, and once you create your pipeline, you can upload it to the Vertex console on Google Cloud, and you can run your pipeline and stuff like that. So I'm gonna leave this in the Slack channel and in the chat if you want to check it out. I think Vertex is going to play a big role in the future of MLOps, and the Google guys have done a great job on that. So we're looking into this heavily as well. So once you build your pipeline, kind of like the pipeline you saw with Qflow, this is how it looks on your Google Cloud console. Kind of the same DAG, the same structure and stuff like that. So you want to check this out. So I'm going to leave a link for this at the end of the meetup. So let's go through a scenario. And this scenario was put together by some of the guys on my team. So a big shout out to them. So the goal is you're trying to a public data sets to predict customer satisfaction and on an airline. So the airline tried to be anonymous, but they provided the data free of charge on cargo. So we have the data sets. So the data set consists of 23 columns, over 120K entries. So the problem statement that they were trying to solve with this data set is to predict what makes a customer unhappy or disengaged. And the satisfaction is not solely based on the flight itself, but also the experience around the flight, booking and landing. So I think guys from Sabre get this right away because that's what they do. So one of the things we tried to do around this was to predict what will make a customer will basically make a customer feel happy or feel disengaged as well. So in this kind of use case, so let's say a company wants to solve this problem. So you have a subject matter expert that will come in and just present the problem to the data scientist. The data scientist basically will go through the problem and understand the kind of problem they want to solve based on the data sets. So to get started, one of the things we do is we do a lot of exploratory analysis. So as a data scientist, you take a sample of the data or subset of the data. You try to do some exploratory analysis, the number of people that are satisfied against and the ones that are dissatisfied. We go through a bunch of analysis. So just imagine yourself as a data scientist. You go through all these analysis, understand in that attributes of the data that you want to basically build your model around. So you can do this on your Jupyter Notebook, on Data Prep, or Data Studio on Google Cloud. So the next thing is like you want to see the attributes that really matter. So this is a correlation plot or heat map that shows the relevant attributes and things that really matter to a customer satisfaction. So once you do this in an organization as a data scientist, you run it by maybe the business owners or the product owners or the SMEs to just see what you've done, and they can give you feedback on based on the output and see what attributes really matter or what you need to drop or what does not really matter in this case. Um, we see that in-flight entertainment has a strong correlation of around zero point 0.52 with customer satisfaction. So 50% of the time, if customers have in-flight entertainment, they probably feel very good. So that's one thing that might be part of your features that you build into your model pipelines and stuff like that. So that takes you to the next stage in an organization. So you want, based on what the data scientist and the subject matter experts or product owner discuss and what features they say are very important. You have the data engineers working with the data scientist. And one of the things you do during your feature engineering stage, which is where you try to prepare all this feature at scale and dump it in the feature store for your model training, is like you want to remove things like outliers, things that are not really relevant, or things that are going to affect your model, and you want to remove them. Null values, dropping or combining column with literal no correlation. So you go back to the correlation graph based on what the data scientist showed you as a data engineer, and you identify all these things that are not like positively correlating or does not really affect the eventual input to your model, and you can drop it off. So all these things are what you do during the process of feature engineering, converting your categorical variables into like numbers so that you can easily fit into just to like your model training input. So outlier removal, I mentioned it as well. So you can do box plots to remove outliers and things that are not relevant. You can drop them off and just do a quick visualization through box plot. So once we've done that, what we do is we'll run a pipeline to like bring in the data and basically run everything through this pipeline. So we'll load the data, we'll do some statistics to see the volume, the number of rows that we dropped, the ones that we kept. We'll make sure we'll validate it against the schema just to make sure things are okay. So we'll get the data, we'll create a schema for it, we'll do a mapping. And after that, we do validation. Then we do feature engineering. That's when we write all this data into our feature store. So that's like an end-to-end feature engineering data pipeline for this use case. So the next thing we do is the model training with ML operators, in this case on Qflow. So basically operators are they're part of Qflow, and the whole concept of operators for you to like wrap up the whole process of training your model into a container, and you can manage and monitor the lifecycle. So they have different operators like TF operators, PyTorch, XGBoost, MPI operators. All these things are open source, and on the Google Cloud Console with Vertex as well, you can basically use a lot of containerized operators as part of your pipeline. Google has some containerized component as well that you can use as part of your pipeline that behave exactly like an operator. So you have all these operators that allows you to train a model. If you're running a TensorFlow job, you use a TF operator. If you're using a PyTorch operator, a PyTorch, you run the PyTorch operator and XGBoost. And there are a lot of operators coming in and out there. So if you're running things like R or a language that's not really common out there, someone might have developed the operator, then you can just grab it and use it and run it as part of your pipeline. So the operator basically runs on Qflow. In this case, we're using a TensorFlow training operator to train our model. So after preprocessing our data, we run it through the TensorFlow operator. And we're initially, I think we got an accuracy of around 88%. So basically, we run the training inside the operator. The operator, we run it multiple times, and I'm going to show you that with hyperparameter tuning. So the first time you run your model, the result may not be accurate, but over time, you run it over and over, and you can select the best performing model. So you do different model scoring, and you select the best performing model from from all the iterations. So that brings us to hyperparameter tuning. So the first time you build your model, there are a lot of things that goes inside your model development that beyond just your data. Things like the number of layers you have for your neural net, the batch size, the epoch, and things like that. They're not part of your feature vectors, but they may affect the quality of the model you produce. So that's where you have people accessing the model, checking out the accuracy, checking it out to make sure things are okay. And that process is called hyperparameter tuning. In Qflow, it's done with Katib. In the Google Parlians, they have with Vertex AI, they have Visor, which is the same thing. There was a paper written around Visor, which is a lot of knowledge around that is into Katib as well. So the whole idea of the hyperparameter tuning is like you want to select the optimal input hyperparameter that will basically help you produce the right model. The number, the epoch, the layers, if you have a neural net, um, the batch size, and things like that. If you don't select the right value, your model may not be as accurate as what you expect. So it's like I kind of like think about it this way. It's like you're trying to like get a right frequency. You have a dial, the old school dial radio, where you try to dial the radio and you just want to key into the right frequency. At that point, the sound flows, you're like in the right station and stuff like that. So that's the concept around hyperparameter tuning. Like all these hyperparameters that helps you model, how can you get the right combination of inputs that will produce the most accurate model? So whenever you're training a model, the first time you're probably not going to get the right accuracy, and you want to run multiple experiments over and over. So how can you automate this process so that you have the most accurate model put as part of your training process? So that's the concept of hyperparameter tuning. So once you've built your initial model, you have your data flowing, you have everything going on, you're gonna go through this step, and that's what you do to like get the best model. So you tune the model over and over until you get the model metrics that you're looking for. In this case, it could be like maybe minimizing the loss, increasing the accuracy, and stuff like that. Whatever metrics you've defined and you want to optimize for, you need to do a lot of hyperparameter tuning. So this is one of the things you do before you put your model in production. So once you've built your pipeline, you may run several iterations until you get to the sweet spot, and that's when you promote the model to production. So this is the way it works. You have all these hyperparameter combinations, and you basically want to combine the right hyperparameter to get a right score. In this case, this will be the model that I select because I have the right score. So hyperparameter tuning is difficult. It's kind of like you're running your model like 1,000 times manually. So there's a tool to do this on Qflow called Katib. There's an equivalent of these on Vertex called Visor that does the same thing, that allows you to like train your model and basically select the best performing model. So with Katib, they support all these languages and different hyperparameters in the search space that you can use. So the combination of all these hyperparameters, it could be like exponentially factorial because you have different combinations. So there are different combination schemes, which is a search-based algorithm. You can do a random combination set. So if you have like 3 hyperparameters, or you can just randomly run your model and try to pick the best performing model. Or you can do a grid search. That's a little bit exhaustive, where you go into all the data points and you try to select the best performing model. Or you can do Bayesian optimization, which is like the power input to your model and the output of the model will determine the next input hyperparameter sets, and they have the hyperband as well. So the key concept is like you have an experiment space, and I'm going to show you that shortly, where once you've trained your model, you have an objective, which is like, do I want to maximize my accuracy? How many models do I need to train to get an accurate model? And you have a search space, which I just talked about. So you can do an exhaustive search where I want to try all the possible combinations of input hyperparameters that will provide the right model, or I just want to do a random selection. So I want to like just try this random number, and once I get to my objective function, which is what I'm trying to optimize against, that optimize for, then I can just end the process and stuff like that. And you have different search algorithm that will allow you to like search the space and select the right model performance. So Visor does this. on the Google Cloud and in the Qflow environment, you can do this with Katib. So this is how we basically run a Katib job. So once I've trained my model, I want to get a right input hyperparameter before I throw that model into production. So I'll launch a Katib experiment and I'll run my training. And once I have the right model, then I'll just export the model and I'll check the results. So this is a sample experiment run, but let me go to the Qflow dashboard and show you how that looks. So this is my input hyperparameters. I have accuracy, I have learning, this is my objective function, the accuracy. But these are my hyperparameters, the learning rate, the batch, and these are the optimizers. So for those of you who have done things around Keras before, you have the SGD and Adam optimizer. So they're like categorical variable. You see that all. So what I'm trying to do in this case is like I'm trying to train my model using different kinds of optimizer, either Adam or SGD, and I'm varying the batch size and I'm varying the learning rates. So these are the variables, but I want the combination of these three attributes that will provide the most accuracy for me. So imagine you're trying to do this by hand. It's very difficult because you need to run your model several times and it could be boring. So, but if you have an MLOps process in place, you can automate this either on Vertex or on Qflow, like I'm showing right now. So you have these input hyperparameters, the optimizer, the batch size, and everything. So each path is a combination. So if I follow this path and select Adam optimizer in my model, and I pick a batch size of 99 and a learning rate of 0.009 in my model, and I run the model several times, I'm going to end up with an accuracy of 0.9, which is not good enough because I want to select the most accurate model. So it's going to do like a lot of runs. Like imagine you're running your model several times. So you do all these runs and you want to select the most accurate model. So if like your cutoff point, then there's a trial budget. So all these paths are different tries of the experiments that you're running. So if you exhaust your trial budget, you can cut it off. Or if the model accuracy is not good enough, you can do something called early stop. You just shut it down. It's a waste of time. But you can, I mean, so but if you have your objective defined, like, okay, I want to have an accuracy greater than or equal to 0.92. So you just keep running until you hit that accuracy, and you can do several runs until you do that. And once you do that, then your model, the training stops, and you can just take that model, and you can have an API that deploys it into QA. They can test it, make sure things are accurate, just like you found out after running the training and inferencing. And once it's accurate, then you can push it into production. So a lot of all these things are what people do manually by hand, or you just select a bunch of combinations of input output parameters and you assume that the model is going to do right. So people do that a lot, but all these things can be automated with Qflow. And if you're using Vertex with Visor, which is part of the Vertex AI platform as well on the Google Cloud. So after hyperparameter tuning, we're able to like push the accuracy from 88% to 92.1. So the initial training, once we set up the pipeline, you have your feature vectors, you have your model, everything runs end to end. The first model was like 0.88, but once you now run all these trials and experiments on your pipeline, because you have everything laid out, you have your data engineer running this with your ML engineers, you can drive or increase the accuracy. So in this case, the objective is to have an accurate prediction. So we just run it several times until we hit our accuracy. So the other part of this is care serving. And in the Qflow pipelines, there are different serving mechanisms. So you can serve your model with there are a lot of contributions to the open source serving tool. There's something called TF serving, KF serving, and Seldon call. Basically allows you to like containerize your model and just serve it as an endpoint because that's how you want to serve it. So you can now, what we've done in this case is like you create a model, you wrap it up, and you can now serve the model through an endpoint. So you send an API request to the model, you get a prediction output. So that's what the model serving does. And in the Vertex environment, they have something called the endpoint that basically allows you to deploy your model and just serve it through the endpoint. So you send the data to the model, you get the endpoint results. So this is the way it looks in the Jupyter notebook. Once you deploy your model, you're going to have an endpoint that looks like this. And from that endpoint, you can basically monitor when it's ready. And once it's ready, you can make an API call to it and get a result back. And once you get a result back, you can see the results of your prediction. So at the end of the whole process, you have a training, feature engineering. After feature engineering, you do your model training. After your model training, you do your hyperparameter tuning to select the best performing model that you can use in production. Then you do your model serving, which is what you're doing with KF serving, predicting what's right for your model. I mean, basically checking the output of the prediction and making sure the results are okay. So, so the overall enterprise ML goal, to wrap this up, is it looks like this. As an ML engineer or practitioner in the MLOps space, you're going to build components and pipeline. So that's what this is all about. So you build all these components. You can either run it on Google Cloud Advisor or run it on Qflow. These components are compiled into pipelines. So basically, you compile your components, which in the case of Vertex, it becomes like a JSON. In Qflow, it's YAML, and those pipeline gets uploaded to your Qflow environment or your Vertex environment. And the next thing you try to do once you've built your pipeline, because you've now created a flow pipeline from fetching the data to training the model and stuff like that, the next thing you do is now hyperparameter tuning. So you want to like select the best model, create the best model from your process, which there's a lot of dependencies. In this case, you have your data dependency, you have your source code dependency. So you do your hyperparameter tuning, run it several times. You have different versions of your pipelines, creating different model output. And while you're doing this, you're monitoring things to make sure you have the right model that comes up with like the most accuracy if that's your objective function. And after that, you deploy. You do your model serving, which is where you publish your model, and that's where you consume your model. It becomes something that you can consume on smart cars and mobile phones and things like Nest. In this case, we're doing prediction and stuff like that for airline. What determines the customer satisfaction based on all the selection criteria that we've trained our model on. So that's the overall goal whenever you're trying to operationalize the ML process. And you have similarities of this in other cloud providers on Google, Amazon, and Azure, but the underlying common denominator whenever you're trying to operationalize an ML workflow just basically looks like this. I think that's it. Any questions? Thank you.
All right. Yes. Now that was was a nice overview. I think behind the two words of ML, there is a lot of components hiding behind there. So people throw around machine learning and ML and MLOps, not flippantly, but once you peel back the covers, there's quite a few things there. But it looks like there's lots of tools that make it easier than trying to build all your own infrastructure and make it roll on your own.
Yeah.
So we do have the Q&A tab open. We do have the Q&A tab open if there are questions. We don't have everybody's mic hot here. And if there aren't questions right now, I do have a few questions I'd like to ask presenters. And definitely thanks again for joining us. All right, here we got Ramji coming in with another one. Ramji says, and I'll read it out loud for those that couldn't join us and will be maybe watching this later. Question from Ramji Bala: how many companies, in your experience, have a mature ML practice?
It's happening. I think if I go back the slide I showed in the last like 3 years when people started taking all these things serious, because prior to this, the way it's done is like you build a model, you try to wrap it up in Docker, Fast API, Flask, and you try to put it out there. It works. But the challenge with that is like once you start having a lot of people hit this microservice or API, it buckles and it creates a lot of problems. You're not able to scale all these things. So I would say in the last 2 to 3 years, there've been a lot of traction in this space, and many thanks to Google. They're doing a lot of innovations around this. They started the Qflow projects. They were the one driving it front, right, left, and center. And now they have the Vertex implementation, which is a lot more robust, and it's going to go a long way in helping a lot of organizations to get into this space. So I think it's something that is getting a lot of traction lately, and it's very interesting. Yeah.
All right. Yeah. So it sounds like building models might have been the not the easiest part, but building models. You get the model, deploy the model into production, and then be able to keep up with the requests to the model was hard, and without either crashing because you had too few resources or spending way too much money because you had too many resources. So with the managed services being offered up from the cloud providers, it's Google Cloud in particular with Vertex, that it sounds like it's becoming. You don't have to be a magician to make it happen.
Sure. Yeah.
All right. All right. Let me pick one from the list. And this will be not a. This will, and I'll divert from MLOps area and kind of get into maybe a couple questions about your journey to kind of where you are now as a MLOps practitioner and with MavenCode. What would you think? What would you say is the biggest risk that you've taken professionally? Or maybe it doesn't. Maybe not just professionally, but you can.
In general, yeah. I think we want to stay with the professional part. It's just the risk of being on the edge, because it's like you're betting on the future.
Yep.
You don't really know if things are going to go your way or go in a different way. Kind of like we're talking about Qflow. All those things started up like 3 years ago.
Yep.
And very few people knew what's next, and now it's becoming a big thing. So it was a huge bet career-wise. As someone working in the big data cloud space, to want to do things around MLOps, which was just a paper topic. It was a publication like 6-7 years ago. So I also like staying on the edge, trying to learn all these new things. Sometimes people go in that direction, and sometimes things just shift and goes in a different direction. So also living on the edge is kind of what I do, trying to understand the next new thing and know what I can do with it or what I can do with it.
Okay. Yeah. So trying to stay on the technological bleeding edge. It's hard to know if you've picked the right blade to lean on, the right edge to lean on.
Yep.
All right. How about one more? How about on early career choices? If anybody's kind of early in the career, how would you say your early career choices kind of led you to where you are now? Maybe it's not a linear path, but any of the choices that you made earlier, do you see them leading you kind of to where you've been at? Obviously, you have some little bit of adventurous, living on the edge of technology, but any other choices that brought to where you are?
Oh yeah, sure. Basically, for me, I'll say trying to understand a lot of all these new things and learning a lot from people that do it. I think it simplifies a lot of things for you. Google solve a lot of problems at scale. So if you're trying to do something at scale, you want to understand their technology, understand their stacks. A lot of all the things that Google does or all these big companies do, they try to they publish papers on it 4 or 5 years before it actually materializes. So checking out all those things when they're still in the incubation stage or the research stage where people are not really paying attention.
Hmm.
A lot a lot of all the problems around self-driving car, autonomous cars, image processing and segmentation and stuff like that. Those are like research topics like 4 or 5 years ago.
Yep.
So basically, spending some time on these whenever you have downtime, just understand where people's head are and what people are thinking about. I think
Hmm.
it's helped me a lot in terms of the next career choice I try to make or the next technology stack I need to learn and stuff like that because it's like a Pandora box. You can't know it all
Yep.
and things like that. The other thing is I try to network a lot, try to identify people in the space I am, doing the
Sure.
same thing, going in the same direction. And I do a lot of meetups, go to conferences and try to give talks and listen to people and see what they're doing and where they're going. I think it helps a lot. The networking aspect is a key component of my career. Spent I spent a lot of time going to conferences and things like that. So I think for anyone just getting started and you want to go far, I think there's a proverb that says if you want to go fast, you go alone, and if you want to go far, you go with people or something like that. So I think that's very important.
Okay. Yeah. No. That. Yeah. Building that network of people. There's some information flow and opportunity.
Yeah,
That flows through networks.
that's
That
right.
actually kind of leads into a little bit to what I was thinking of for the next question. 'Cause, as and this was so for early careers. Yeah, definitely technical skill is important, but don't forget to do the networking and looking ahead and reading on other things.
That's right.
If you're talking to somebody that's maybe uh, started, maybe they're a developer or maybe they're in on the operations side, but they wanted to get into kind of the machine learning space. Do you think there's one of the positions in that whole chain of that whole team that's part of the MLOps team? Is there one that's kind of an entry level ish, easier to get onto to get into that, just to get into that ecosystem, or where would you kind of point people
Yeah,
to try and to start out?
yeah, sure. That's a good question. So one of the things I do a lot is I follow a lot of open source projects.
Hmm.
If you're trying to let's say get into Qflow, or just go into the Qflow GitHub and you might just be documenting stuff or correcting stuff or testing stuff. And over time, people recognize your input, they value you, and you can basically try something out. If it breaks, you raise a Git issue, and someone comments on it. Or if someone is having a problem and you've encountered it before, you try to volunteer and help that person out. So if you're trying to get into this space, the easiest way to get in is through the open source channel, I believe, because a lot of things I learned about Qflow and a lot of things I've done with it is through the open source community.
Okay.
And eventually, when Google decided to go in direction of Vertex, you can see a lot of similarities between what's in Qflow and what's in Vertex because a
Hmm.
lot of most of the engineers that worked on Qflow are the ones who implemented Vertex. So uh, you can easily see all those similarities. So if I decide to go in and build things in Vertex right now, which I'm learning as well,
Yep.
it's easier for me to just migrate that knowledge or transfer that knowledge to what Google is doing on Vertex and things like that. So the easiest way for anyone to get into all these things is the open source community. You can go in, maybe start documenting stuff. Eventually, you understand the code. You can start contributing patches, and eventually, you can become a code reviewer, comment on
Yep.
people's code, create feedback, and eventually, they have a conference. Most of these open source projects, just go to the
Hmm.
conference and socialize and get to meet the people you chat with or comment on their codes online in person, and you form a network. And if something comes up, they'll call you up and they want to hire you if you're looking for a job and things like that. So I think that's one of the things I do a lot. Yeah, and it's been very helpful for me.
Okay, yeah, it's become part of the open source community that's
Yeah, the ecosystem.
that you're trying to try to get into. Try to be helpful. Try to be helpful. Provide something, and kind of connect in by kind of offering up. You may not know everything at the beginning, but like you said, you could start just doing some code reviews. Maybe there's something misspelled or is not clear. You can you make the pull request, see if it gets accepted, and start joining in. Definitely thank you, Charles, for joining us.